So in a previous lecture, we have studied angular momentum. We have also discussed how to calculate the initial position vector, angular displacement by using Lagrangian equation of motion. So now we can also check whether the energy is conserved in a central force field or not by using the same equations. So I'll write here the name of the point, energy conservation by using the Lagrangian equation of motions in a central force field. Okay, see here we are trying to take out the derivative and take out the final equations by using this Lagrangian equation of motion, because in the reference books the equations are given directly. So for a PJ level you must know where the equations are coming from. Okay, so we are trying to give a little bit of explanation behind these equations. Okay, so let us try to evaluate how energy conservation means. This T plus V is equal to E, or this is a kinetic energy, this is a potential energy, this is a total energy. So we have to show this term as a constant. T plus V is equal to constant. Okay, so these are the Lagrangian equations of motion which we have calculated, and this is the derivation for the angular momentum, and this is what we have evaluated, the equation for the angular displacement. Now just put this value of this theta dot in this equation, and what we are going to get is m r double dot minus m r dot L square m square r raised to 4 plus dou v upon dou r is equal to 0. So this is not r dot, so this is r. So what I'm going to get, m r double dot minus L square upon m r cube minus dou v upon dou r is equal to 0 plus. Now so let us replace this term by dou r of minus L square upon 2m r square. See, so what will be its derivation? Its derivation will be minus L square upon 2m r raised to minus 2 into this dou by dou r. I can also write this as minus L square minus 2 r raised to minus 3 upon 2m, which will be equal to this 2 will get cancelled, so this will be L square upon m r cube. So this minus 3, if that come to the denominator, it will become r raised to plus 3. Okay, so this equation is not having any physics explanation, so these are the terms which are coming directly from the mathematics. Okay, so we just want to take this in this form, that's why we are doing some mathematical arrangements to get this equation. Okay, so what we need to explain, we need to explain the energy conservation by using the Lagrangian equation of motion. Okay, so the few mathematical arrangements are going on here. So I will exchange this term by this term. So what will be my equation? M r double dot plus dou by dou r of L square 2m r square plus dou by dou r of v is equal to 0. I can write this mr double dot plus dou by dou r L square upon 2m r square plus v is equal to 0. If I take this on the right hand side, m r double dot is equal to minus dou by dou r of L square upon 2m r square plus v. If I multiply both the sides by r dot, what I'm going to get is dou by dou r of L square upon 2m r square plus v into r dot. So this r dot is nothing but 2m r square plus v, that is nothing but dou r upon dou t. Now this dou by dou r and dou by dou r, that will cancel out, and what I'm remaining with is minus dou by dou t of L square upon 2m r square plus v is equal to m r double dot into r dot. So the last equation is m r double dot r dot is equal to minus dou by dou t of L square upon 2m r square plus v. This is the equation which is written below over here, which we cannot see actually. So this is the last expression. Now so again we are trying to do some mathematical arrangements. So which is d by dt of 1 half m r dot square is equal to 1 half m into 2 r dot into r double dot. So these two will get cancelled, and what I'm going to get is m r dot r double dot. So I can replace this term on the left hand side by this equation, and I can write d by dt of 1 half m r dot square, taking this right hand side term also on the left hand side, and I am changing this dou by dou t to the d by dt of L square plus 2m r square plus v is equal to 0. I can replace this L square, or I can put the value of this L as m r square theta dot square, and when I do this, d by dt of 1 half m r dot square plus d by dt of m square r is to 4 theta dot square upon 2m r square. This 1m will get cancelled, plus v is equal to 0, and what I am left with is d by dt of, I will take 1 half m common out of this, or I will write 1 half m r dot square plus r square theta dot square plus dv by dt is equal to 0. Now this term, or I will write this d by dt of 1 half m r dot square plus r square theta dot square plus v is equal to 0. Now if the derivation of something is 0, then that term must be constant, and this term is nothing but this is the kinetic energy which we have calculated in a previous lecture, and plus this is the potential energy, and which is equal to constant, and which we want to prove this T plus V is equal to constant, which is equal to total energy. Thus, from the Lagrangian equation of a motion, energy conservation in a central force field is proved.